Now, we've learned that e to the at sine kt is k over s minus a squared plus k. And then Laplace transform of e to the at cosine kt is s over s minus a squared plus k squared. Actually, s minus a. So these are the known Laplace transforms. But solving a few differential equations taught us that not only you want to know how to go this way, but you also want to know how to go backwards. Okay? And therefore, let's try to figure out the following question. Example, find the Laplace inversion of, let's say you have 5s plus 3 over s squared plus 4s plus 13. Let's think about the following question. And this is a good example because after doing this, then you'll be able to tackle the ones that have e to the at cosine in there. Okay? Let's try this. Okay. The question is asking that if you get the result of some Laplace transform as this, what was the function that produced it? That's basically the question that's being asked here. And this one is written so that it will be the sum of this one and that one. Okay? So that's why I wrote only these. Okay. First, I want you to be able to think about this in this form. Okay, I want you to be able to rewrite the denominator in this form. I want to be able to rewrite this denominator into something squared plus a number squared. Now, where did we learn something like this? What was this thing called? In pre-calculus, we learned it as?
Complete the square?
Completing the square, yes. So that's what we have to do. And the way you do it is as follows. What you do is take the coefficient of 4, divide it by 2, and that gives you 2, right? And then you square it by 2. Okay. Take the power of 2. This means you take the power of 2, maybe I should say. Power of 2, and 2 squared is 4. Get it? Okay. Oh, no. You don't have to square it. That's not the method I'm using. Just divide by 2, okay? So just keep in mind what this number is. And here's how you're going to think about it. Write down this s and then this number. If this happens to be minus, then it'll be s minus something, okay? And put it as squared. Then you ask, what should fit in here? So it's 4 divided by 2, it's 2, positive 2, and your question is, what should go in here so that this matches with that? Well, look, 2 squared gives you what? 4. 4 plus what gives you 13? 9. So you put 9. That's called completing the square. Now you might feel that this way of completing the square is somewhat easier than how you experienced it in pre-calculus. That's because the method I'm telling you right now is only valid for the case when s squared's coefficient is 1. Right? So if it's not 1, then you first have to divide by 1. And especially when you have fractions, it's going to be a harder one. Okay, let's digress a little bit and think about some other examples. So if you had, say, s squared minus 6s plus 25, what is this? Divide this by 2, so what do you write?
-3.
S minus 3 squared. Negative 3 squared is 9. 9 plus what gives you 25?
16.
16. So that's it. That's how you complete the square. You can do this, right? Okay. All right, back to our question. All right, then you say s plus 2 squared, 9 is 3 squared. And that's good because now it's in this form, right? So here's our goal. I want to express 5s plus 3 over s plus 2 squared plus 3 squared as something of this type and something of that type. Now, before I go on, tell me what a is and what k is. Compare this to this bottom one. If I say this is equal to this, what's the value of a?
-3.
No, s minus a is s plus 2, so a must be
-2.
-2. K must be 3. K, by the way, is positive, okay? K must be 3. Is that good? Right. So, this thing will be of this form, 3 over, actually, let's put the cosine first. This thing will be s plus 2 over s plus 2 squared plus 3 squared. And the second thing will be 3 over s plus 2 squared plus 3 squared. Okay? And we say it's a times this plus b times this. And the reason I'm separating this and giving you this as a separate example is because the way we're splitting this is somewhat different from the way we learned it for integrating. For integrating, we simply learned to do it like s plus 2 squared plus 3 squared, and then you put as plus b, right? That's how we learned it when we were doing this partial fraction expansion in Calc 2. But because we actually want to use this for inverse Laplace transforms, it's much more complicated. It's a times s minus a and b times k. That's the way we have to figure it out. Okay? Now let's move on further. Afterwards it's similar. You multiply this to the other side, you get 5s plus 3 equal to a times s plus 2 plus 3b. Right, if you multiply the denominator, that's what you get. Now what would you do? SS, plug in -2 so that s go 8. This becomes 0. It'll be 8 times 0. -10 plus 3, so it's -7 equals to 3b. Giving you b equals to -7 over 3. And then if you compare the highest order term, 5s has to be as, right? On the right side, the only s term is a times s. Right? So as and 5s gives you that a must be 5. And you're almost done. Now what do you know? You know that 5s, you know that 5s plus 3 over s squared plus 4s plus 13, the thing that we were given, is now equal to 5 times s plus 2 over s plus 2 squared plus 3 squared plus -7 over 3 times 3 over s plus 2, s plus 2 Sorry, let me write this again. It's hard to read. So 5s plus 3 over s squared plus 4s plus 13 is equal to 5 times s plus 2 over s plus 2 squared plus 3 squared plus negative 7 over 3 s plus 2 over times 3 s plus 2 squared plus 3 squared. And I know that this is a Laplace transform of what?
Cos.
A is negative 2 and k is 3. So what is it? E to the negative 2t cosine 3t. Right? What's this? This is a Laplace transform of e to the negative 2t sine 3t. Therefore, what's our final answer? Answer is 5 times e to the negative 2t cosine 3t minus 7 over 3 e to the negative 2t sine 3t. That's it.